All right, here I actually have two lessons in one, lesson 6 and lesson 7. They are both very quick, although lesson 7 will take us a little bit longer as we will work through a couple conversations of how to draw our pictures and how to be patient with visualizing this process. So lesson 6 is kind of interesting. This one I probably should do with lessons 3 and 4, but we'll see kind of how this pans out. But essentially, we have a situation where we can have congruent right triangles based on knowing the lengths of two of the sides. Essentially, this is rooted in the Pythagorean theorem, and we know that a squared plus b squared equals c squared gives us some special constraints, that if we know c and we know a, then we can find b, or if we know a and b, then we can find c, or if we know a and C, then we can find B, or vice versa, or whatever I didn't say. And so the goal there is to recognize that if we have two pairs of congruent sides in a right triangle, then we do have a pair of congruent triangles. Essentially, we are going to use what's called the hypotenuse leg theorem to prove that right triangles are congruent. So this is rooted in what's called the HL, or hypotenuse leg theorem. And it has to do with right triangles exclusively. Obviously, here we have two sides of a triangle that are perpendicular to each other, and therefore we know that this is a right angle, and therefore this is a right triangle. And in this right triangle, the side that's opposite from the right angle is our hypotenuse, and then the other two sides are called legs. So similar language that we used with isosceles triangles, that the two congruent sides were referred to as legs. Here, the two sides that make the right angle are referred to as legs. And so hopefully that language is a little bit familiar to you. But you understand that, that the lengths, the sum of the lengths of the two legs, the sum of the squares of the lengths of the two legs is equal to the square of the hypotenuse. And so we do have some constraints there based on that Pythagorean theorem that we already know and understand from Algebra 1 and pre-algebra. But here is Theorem 6 from this unit. The hypotenuse leg theorem states that if the hypotenuse and a leg, just a single leg of a right triangle, are congruent to the hypotenuse and a leg and another right triangle, then the two triangles are congruent. And here's the reason, folks. And I'm not going to do a whole proof of this just because it's not necessary. But if I say that this is a right triangle, and I say that this is a right triangle, where we have a pair of legs congruent and a pair of hypotenuses congruent, then what we have is essentially that angle side side, or side side angle, that is not a shortcut that we are allowed to use, right? But since this is a right triangle, it doesn't matter what the lengths of these sides are. If this is A and this is C, and this is the same length and this is C, then to find x and to find y, we're going to use the Pythagorean theorem and basically find out that x is equal to the square root of c squared minus a squared, whatever that length is, whatever c and a are, and y is going to equal the same thing, the square root of c squared minus a squared. All right? Taking a squared plus y squared equals c squared, subtract a squared from both sides, take the square root on both sides. All right, so I did some algebra there. But basically, these are equal to the same thing, so these lengths have to be equal to each other. Essentially is the proof of this theorem. However, we don't have to do that proof today. What we're going to do is we're going to walk on assuming that this is true, and we are not going to do that work necessarily to say that we have side-side-side congruence. Instead, we're just going to say, hey, if we've got a right triangle, and we've got a pair of hypotenuses and a pair of legs congruent between them, then we know that we are talking about congruent triangles. So here we go. Given that segment AD is the perpendicular bisector of segment CE, and also given that segment CD is congruent to segment EA, prove that these triangles are congruent. So essentially what we're going to do is we are going to go through a series of steps. First of all, you can probably recognize that we have a pair of, these are going to be a pair of congruent angles, these are going to be a pair of congruent sides and a pair of congruent sides. Well, I cannot use side-side angle or angle or angle side-side here. It's not going to work. Instead, we're going to have to use hypotenuse leg. But in order to use hypotenuse leg, we have to make sure that we are dealing with a right triangle. So we're going to use this information first. Step 1. AD is the perpendicular bisector of segment CE. Now, this tells us two things. One, it tells us that these angles are right angles. That's huge because that means that now we're dealing with right triangles. Also, it bisects segment CE, so it means that segment CB is congruent to segment EB. That's the definition of bisect. So there's two things happening here. I'm going to focus on the angles first. Not that they're congruent angles, but that they're right angles, which means that these triangles are right triangles. All right, so I have two steps that are going to come after this. That are first going to say angle CBD and angle EBA are right angles. That is my next step because that's the definition for perpendicular. Next, I'm going to say that these triangles are right triangles because they have a right angle, right? They each have a right angle. So that's the definition of right triangles. Next, I'm going to use the bisect part to say that CB is congruent to EB. By the definition of bisect. Here's a situation where we used three definitions in a row. The definition for perpendicular, the definition for right angles, and the definition for bisect. All right? We are also given that CD and EA are congruent. And therefore, we have hypotenuse, we've got legs in a right triangle. Therefore, these triangles are congruent. And the reason there is the hypotenuse leg theorem. And we can just write HL. All right, so this is, that's the end of lesson 6, which basically says if you have right triangles, then you have special situation. You are going to use these types of statements, all right? You're going to be given that something's perpendicular, that means you got right angles, that means that you have right triangles. Only if you have right triangles can you use the hypotenuse leg theorem. You cannot use hypotenuse leg unless you make a statement about those triangles being right triangles, all right? So I know that might be a little bit of some extra steps that might seem, why do I have to state that? But again, you are making statements that everybody can read and understand, all right? And so that is the goal of doing any proof, is that you can read through the proof and you can understand what it is telling you, all right? And so that was lesson 6. Moving on to lesson 7, we are talking about applying like other applications of CPCTC, or that definition of congruent triangles. Essentially, we're dealing with these overlapping triangles that have a reflexive part congruent. So our job is to identify congruent overlapping triangles, but then use that information to prove that other triangles are congruent. So we're going to have a pair of congruent triangles that's hopefully pretty easy to deduce, but then we're going to apply that information to prove that another pair of triangles in the same figure are congruent. This is like the pinnacle, all right? If you can do 4-3 and 4-2 and 4-4, all right, basically using the secret shortcuts, and 4-6, I suppose, using the 5 secret shortcuts for triangle congruence, and then apply CPCTC, folks, that's where I want you to be, all right? But here, this is that next iteration. And so some of you are going to wrestle with this, and that's okay. But what I really want to do is I want to push some of you to have a little of a more enriching experience here. So that's kind of what we are referring to in this case. So the first step is to identify common parts. So basically, this is our given figure. And in this given figure, what we should notice in this weird kind of quadrilateral that I don't have this point named because it's kind of irrelevant in our picture here, but in this awkward quadrilateral, we notice that we actually have what looks like 2 overlapping triangles. All right, we've got this triangle right here, GDF, which is drawn right here. And then we have this other triangle, GHE, which is drawn over here. Part of our steps today are going to be taking a picture like this and redrawing it like that. And the reason why we want to do that is because we want to see that in these pictures we have a common or shared part, whether it's a common angle or a common side. And so identifying that common piece means that if I'm trying to work with these 2 triangles and I'm trying to show are these 2 triangles congruent to each other, one of my statements is going to be that angle G is congruent to angle G. it's a different angle. This is angle DGF, and this is angle EGH, but I can call them both angle G, and they're the same angle. It's actually the same angle in this original picture. So this angle and this angle are congruent by the reflexive property of congruence. All right? Identifying that common part is a little bit tricky visually. All right? And so that's what we're going to focus on. In this particular situation, what I want to do is I want to prove that ZW is congruent to YX. That's my goal. All right? I don't have that information yet, but this is what I'm going to prove. I am given that the big angle at W, so ZWX, so that's the one that's marked twice here, is congruent to the big angle at X, YXW, the big angle there. I'm also given that the little angles at W, so YWX and ZXW, are congruent to each other. So that's what those markings are referring to, and that's what these given statements are saying. Well, in order to really visualize this well, what I want to do is I want to redraw those triangles. All right, I want to draw ZWX, and I want to draw YXW, and I want to label what I know. I know that the angle YWX and the angle ZXW are congruent. That's what I am given right here. All right, I also know that ZWX, the big angle, and YXW, the big angle over on this part right here, are congruent to each other. Now, what we ought to notice is that this segment right here is the same segment in both of these triangles. All right, so being able to draw those separate triangles is huge, first of all. But second of all, recognizing that WX and XW are the same segment is the key to proving that these triangles are congruent. So here's what we are going to do with this. I'm going to show that that these angles are congruent, because that's given information. I'm going to show that these sides are congruent by the reflexive POC. So I have angle side angle congruence. I'm going to start with, this is going to be step 1, this is going to be step 3, but step 2 I'm going to use that reflexive side that I've got over there. Essentially that's going to be my proof. So angle ZXW congruent to angle YWX, because they told us. I'm going to say that that XW using this order is congruent to WX using that order by the reflexive POC. It's the same segment. The other pair of angles are given, angle ZWX and YXW. That's these two. Given information. And therefore these triangles are congruent. By angle side angle. ZWX and YXW. All right? Now, because those two triangles are congruent, I can prove this. That segment ZW is congruent to segment YX using CPCTC, or the definition of congruent triangles. Again, whichever method you're using. If you're saying definition of congruent triangles, that's great. If you're saying CPCTC, that's great. You don't list both. All right. So that's kind of the goal, is to make sure that we can go ahead and prove that those segments are congruent. Now, some of us, if we are kind of haphazardly trying to do this, we're going to talk about how there's like vertical angles congruent and other garbage, and that's not necessary here. All right. However, I can prove later on. I can prove that this triangle is congruent to that triangle. I don't have a name for this point right here, and that's intentional because I don't want us focused on that right now. But what I can show you is that if I know that ZW and YX are congruent, and I know that the angle at Z and the angle at Y are congruent by CPCTC, and by CPCTC, then I know that these angles are congruent using the vertical angles theorem, then folks, that means that these two triangles, these other two triangles are congruent using a pair of vertical angles, a pair of CPCTC angles, and a pair of CPCTC sides. All right? And so that's kind of a unique trick of proving a pair of triangles congruent so that you can prove another pair of triangles congruent. It's a fun little shtick that you can do in geometry. And again, this is upper tier. This is, you know, if 20% of you get this, then I'm super happy. But it is something that I want to challenge you to understand. It is hard though. And mostly it's tough because you have to visualize it and you have to understand what parts are reflexively congruent to each other and how can you take that to the next level. All right. Again, we're going to do that here, and this one we can do in a couple different ways. So just what we did minutes ago, we're going to take the given information in the picture. There's nothing given stated, but we're going to take the given information in the picture to show that we can prove that these two triangles are congruent to each other. All right? But first, we're going to show that there's other pairs of triangles congruent here. And understanding what we're dealing with is really the trick to this right here. And so what I want to show you is that we can prove that these two triangles are congruent by showing a little side, angle, reflexive side, side, angle, reflexive side. So these two triangles are congruent. That means by CP/CTC that this side is congruent to that side. All right? Furthermore, we can show that the big triangles are congruent to each other, and we can use CP/CTC there. Again, we'll use side, angle, and then big reflexive side, the whole QS, congruent to QS. And then use CP/CTC again to show that these are congruent to each other. All right? And then that would give us hopefully enough information to say a pair of sides, another pair of sides, a reflexive side in the middle, so we have side, side, side. We could do that shorter and ignore these triangles completely, focus on the big triangles, and use CP/CTC twice to say that these sides are congruent, these angles are congruent. And then we could have a reflexive side, pair of CP/CTC angles, pair of CP/CTC sides. And so I think I'm going to do that just because it's a little shorter. And so let's take a look at this situation. Basically what I'm going to do is I'm going to envision this as just the big set of triangles. Here's S, here's Q, here's P, here's R. We know that that information is true. So I'm going to start by saying that PS is congruent to RS, and the reason for that is it's given in the beginning. We have angle PSQ congruent to angle RSQ, that is given. And then I'm going to say that this side is reflexively congruent to itself. SQ congruent to SQ. And so that leads me to say that these big triangles, angle PSQ and triangle RSQ, are congruent by side, angle, side. All right, but now that these triangles are congruent, I'm going to take this a step further and say, by CP/CTC, I know that this segment and this segment are congruent, and this angle are congruent. All right, so that's going to be my step 5. PQ is congruent to RQ, and angle PQ, I'll write it on the next line, angle PQS is congruent to angle RQS. The reason there is definition of congruent triangles. All right, which means if I apply that to the previous picture, I can show that these two triangles, I'm going to erase this part of the picture, and I'm going to put point T into the picture. I'm going to show that these two triangles are congruent using side, angle, side. QT is congruent to QT. Pair of sides, pair of angles, pair of sides. Those triangles are congruent. So here we proved one pair of triangles congruent, so we could use CP/CTC to prove another pair of triangles congruent. Folks, this is a tough proof. I want you to watch each of those steps, review it if you need to, so you can see it a second or third or fourth time to make sure that you feel good and groovy about it. All right, that is the end here. Hopefully you can identify those overlapping congruent parts. Here in this last picture, we had the angles at Q in the big triangle were the same as the angles at Q in this little triangle, and the sides PQ and RQ were in the little triangle as in the big triangle as well. So those overlapping or shared parts are sometimes valuable between those separate figures. And of course, proving a one pair of triangles congruent to show that another pair are congruent.